Alright, hello everyone. Welcome back to Deterministic Operations Research. We're starting to get into sort of how we solve linear programs. We're in the primer stage, talking about the different types of solutions we could see. And that includes, of course, not having any solutions. So let's get into it. So the possible outcomes of linear programs. First off, they could have no solution. This is pretty obvious if you remember from linear algebra. When you're solving a system of equations, it's possible for that system to not have any solution. So it's not a stretch to understand why a system of linear inequalities may also not have a solution. We see here, if we just have a fairly obvious system, two constraints with the same left-hand side, but opposing inequalities to the right-hand side, we're not going to have any intersection of those two half spaces, and so the feasible region is empty. Yeah. Now, a more complicated system may be more difficult to show. So I'm going to call these 1, 2, 3, and of course non-negativity is 4. And we want to show that this system is infeasible. So we can do this by noticing that if a point x bar satisfies 1 through 3, then it will also satisfy a linear combination of the three. Of 1 to 3. You may not be familiar with this exact form of the statement, but if we remember from linear algebra, we solved systems of equations by putting them in a matrix, an augmented matrix, and then performing row operations on them to put them in row-reduced echelon form. Those row operations are in fact linear combinations of the rows themselves. So we're using this statement, this lemma, when we're doing sort of Gauss-Jordan elimination to solve systems of equations. So this is a well-known result. We've used it before, so we're going to use it here. In fact, we are going to take this particular linear combination. This is the augmented matrix here. We're going to multiply these two matrices together, and that's going to give us 4 plus 4 minus 7 x1 plus 10 minus 4 minus 2 x2, etc. which ultimately equals x1 plus 4x2 plus 2x3 equals -1. So, right, that's what that gives us, is this equation. I'm going to call this star. Well, star implies that at least one of x1, x2, and x3 is negative. Because the right-hand side is negative, but the left-hand side has all positive coefficients. We can't add up positives to get a negative, so one of our variables has to be negative. But this contradicts 4. Which is our non-negativity constraint. Now, not every version of this sort of technique will leverage the non-negativity constraints. Your LP may not even have them, right? So what we're doing here is we're trying to combine our constraints in such a way that a contradiction shows up. And if that's achievable, then this is an infeasible system. It's not clear that every infeasible LP has this sort of problem, but if you can identify a contradiction like this, then your LP is infeasible. The second type of solution that your LP could have is unboundedness. So let's suppose that we have an LP and its constraints are these three inequalities. And we can say I've plotted them. Our only variables are x and y, just so we can see them in 2 dimensions. So x and y. And we can see that this LP, or this region, runs off to infinity in the positive x direction. And in fact, I haven't included the non-negativity here, so you could also run off to infinity in the negative y direction. Now, suppose that we have an objective function with this level set. So our objective function could be x. Let's do that. So let's say that our objective is to maximize x. So this level set is just the line at which x equals some value. I'm calling it z here because I don't want to be specific. And we'll take the gradient of this objective. In this case, it's just the derivative to 0, or to oh, it's not. Yeah, it's the gradient of x is just the vector d dx of x, d dy of x, which is, of course, 1, 0, which gives us a gradient, that gradient. So this is the gradient of the objective. And we're trying to maximize, so you may know that the gradient points in the direction of maximization, the most efficient direction of maximization. What that means is if we have a hill, if we think of our function as sort of a hill, the gradient will point straight to the top of that hill, if that makes any sense. So what that means is that we have another level set here. That's going to be z plus something. So z increases in this direction. And it continues to do so. And through sort of just basic common sense, we can see that, in fact, it will continue to increase forever in that direction, and our feasible region allows it to continue to increase in that direction. Which means that our optimal solution is unbounded. It's infinity. No matter what solution we pick, there exists a better solution that is feasible to the region. This is a problem because we can't solve this in the traditional sense. So we need to be on the lookout for problems like this. The book details one way to think about, to identify problems like this. I'm going to show a different one in a second. Actually, I'm going to do that. But first, I want to show that just because a region is infeasible or is unbounded doesn't mean that the problem itself is unbounded. Let's say that we're trying to maximize negative x. Well, then our gradient points backwards. And we have level sets z plus 1 and ultimately z plus 2 at, and we run into an extreme point that is our optimal solution. So we can identify the differences by transforming our problem, our feasible region, into what's called a polyhedral cone. What we do is we take our inequalities and change the right-hand side to just be 0 instead of whatever they were. This means that they will intersect the origin of our space, all of them, and it gives us an idea of what directions are unbounded in this problem. So let's think about our objective function and its gradient again. Clearly, if our gradient is feasible to this polyhedral cone, what that means is we can follow the gradient to infinity forever and continue to increase our function, which would mean that the polyhedron is unbounded. So if the gradient of the objective is feasible to the polyhedral cone, the problem is unbounded. Now notice that only an unbounded region will actually have a polyhedral cone. If the region is closed, what we call compact, if it's non-empty and bounded, the cone will just be the point 0, 0, 0. It'll just be the origin, so there won't be a cone. Now additionally, suppose we had an objective like this. Suppose our objective was maximize negative y. Well, the gradient of that is 0, negative 1, and that points straight down. That gradient is not feasible to our cone, but it is still an unbounded objective, because we can continue to draw level curves, level sets, down, down, down to y equals, upward to y equals negative infinity. Or y approaches negative infinity, I suppose. So, in fact, even if our gradient is within 90 degrees of being feasible to the cone, our problem is unbounded. And there are some more precise ways to describe that, but I just wanted to give you all the basics, the impression of how this works. So here I say it 90 degrees of being feasible to the cone, the LP is unbounded. Otherwise, we have a finite optimal solution. Right, so if we're just past, I'm going to draw a different color. If we're just past 90 degrees, this is going to be the optimal solution of the cone. It's not unbounded, so we have a finite optimal solution, which is what we're looking for. Now, I didn't include non-negativity constraints in this problem just because the cone drops down like this. But if we had non-negativity in this problem, the polyhedral cone would just be the positive x-axis. Does that make any sense? So what we were saying is that y has to be less than or equal to 0, but also y has to be greater than or equal to 0 from non-negativity. Which means that y can only take the value 0. But there's no such upper restriction on x. But that is still a valid polyhedral cone. And it is still useful for identifying the unboundedness of a given problem. And this is possible to do in higher dimensions. It becomes difficult to think about geometrically, just like everything. But you can still do it mathematically by finding what's called extreme rays, extreme directions of a polyhedron. And that's not important for us to be familiar with, so we just want the intuition. Now, there are two more possibilities for outcomes of an LP. The first is a single optimal solution. This is the case for most LPs, and we've covered it at some length. So if we have an objective with a gradient, the largest level curve, level set, will intersect at a extreme point. Right? And that will be our optimal solution. Now, it is possible that there are infinitely many optimal solutions. Can anyone tell me when that might be the case? Alright, so what about if my objective is really, really close to being parallel to a constraint? If it's really, really close, we're still going to get one solution, one optimal. Right? But as we sort of tilt that objective to being closer and closer to parallel to that constraint, suddenly the level curve becomes the last, or the maximal level curve that intersects the set is parallel to that constraint. And suddenly every point on that constraint shares the same objective function value. Right? So in that case, there would be infinitely many optimal solutions. Right? If we had an objective that was directly parallel to a constraint. In fact, if you're in n dimensions, it can be parallel to up to n-1 constraints that are, and you still might end up with infinitely many solutions. So let me show you that in 3 dimensions. Suppose we have an objective function with this level curve. And its gradient points straight out towards this wall, or towards this face of our cube. Well then, that face of the cube will be, well, the maximal level set, the largest valued level set of our objective function, will intersect the whole face of the cube at once. And so all of those points will be optimal. On the other hand, if we have an objective that is parallel vertically, it's parallel in one of its degrees of freedom to these two faces, and it points out towards the corner, well, that maximal level set is going to be this ridge. And we have infinitely many optimal solutions. Now, in all of these cases, we still have extreme points, which are optimal, which is important to us because the method that we're going to use to solve these problems is going to intelligently search through these extreme points of our feasible region and ignore sort of all of the edges and face points, or interior points, as they're called. So if there are infinitely many optimal solutions, there will be at least two extreme points which are optimal. So like I said in the last class, if there is a finite optimal solution to an LP, one of our extreme points will be optimal. So there is one case that I can think of that has infinitely many optimal solutions without having an extreme point. There's one case. Let's imagine, I'm going to duplicate this page real quick. Can I do that? It's not looking like it's going to let me do that. Anyway, I'll add a page then. So suppose we had our same cube, but the difference being that it does not have, yikes, a top or bottom. Right, so these things sort of continue on up and down to infinity in a direction. Forgive my hasty drawing. I was debating whether or not to present this to you. And suppose that our level set of our objective function is again sort of parallel to two edges. I should really get the line tool out. Sort of parallel to our two edges, but it also continues on up and down because the region does. And its gradient is in the direction of this ridge. Well, then again, our maximal level set is going to be that ridge. But there are no extreme points anywhere in this region. So the one exception to our problem, to our statement, where if there's an optimal feasible solution, one of our extreme points will be optimal. The one caveat is that if there are no extreme points, the extreme points cannot be optimal. And if we perturb this objective function at all, we're going to get an unbounded solution, an unbounded LP. So that's one thing to be aware of. This is very unlikely to ever crop up in anything you do. You're much more likely to have an unbounded problem if you have no extreme points. But it is the one caveat that I'm aware of. So if the LP has no extreme points, there may still be optimal solutions. This is hideously unlikely, but I suppose it is possible. So, you may have noticed in the reading that all the example LPs in section 2.1 only had equality constraints. So most of the stuff that we've written and worked with have had inequalities, at least one or two. But these were all systems of linear equations. So for now, we're just going to accept that this math we're going to do now can only be done on systems of linear equations. And then in the next few lectures, we're going to sort of poke and prod at our feasible regions, at our polyhedra, and try to get them to work for this math, with this math. So let's consider a matrix that we have. This could be the matrix for the left-hand side of a feasible region, or of a set of constraints. And we're just going to split it in half, right down the middle. We're going to call the first half AB and the second half AN. And we're going to notice that if this were an equation, we could still perform this operation, but we also have to split our variables down the middle as well. And note that these plus signs are element-wise. Traditional addition is not actually defined for vectors. So what I'm saying here is that if we have x1, x2, x3 plus x4, x5, x6, then the sort of element-wise addition of this is x1 plus x4, x2 plus x5, x3 plus x6. I just wanted to point that out because, again, I'm a picky math major. So yeah. So this is the same whether we split up our things or not. we have the same equation here, because this is going to be sort of 2x1 plus x2 plus 2x3 plus negative x4. Right, that's going to be our first row. Equals 2. And then on the second row, so this is the first matrix multiplication, and this is from the second matrix multiplication. So this comes from here, that comes from here. But that's the same equation we would get if we were to do this matrix multiplication up top. So this is something we can do. And we're going to say, just for the sake of argument at this point, let's pretend that xn, so the back half of our variables, are 0. What happens is that we end up knocking off the second term, and we're left with the first term equals the right-hand side. Now, what we need to notice here is that the columns of A and B are linearly independent. This means that we can invert our matrix AB. You could also do this by row reduction if you wanted to. Row reduction is, in fact, a form of finding the inverse of a matrix, but I'm just going to do it with matrices. I'm sort of behind on my notes. So A inverse AB is just the identity matrix. So this whole term is just going to be xb equals 0, 1/2, 1/6, 1, 0, negative 2/3, 0, negative 1/2, and 1/6 times 2, 1, 1. And this gives us 2/3, 4/3, and 1/3. And that's behind my head. Let me move that real quick. There we go. So then we have a solution to our system of equations. We have x equals 2/3, 4/3, 1/3, 0, 0, 0. That was our full x vector. So this is neat. This is a neat way of solving things, I guess. But for all we know, this just gives us a solution in our feasible region. We don't know that this is special in any way. We'll determine what's special about this sort of method in upcoming lectures. We just need to be aware that we can do this. So the basis, or a basis of a matrix, is a maximal subset of linearly independent columns of that matrix. So if we come back to this page, we remember that these columns are linearly independent of each other. This just means that we can't write we can't write any of the columns as linear combinations of any of the other two columns. Which means that we can invert the matrix, assuming it's square. Additionally, you can only have n linearly independent vectors in Rn. So in Rn, so in the set of real vectors of length n, the largest set of linearly independent vectors has size n, or cardinality n, if you prefer. Which means that a maximal subset of linearly independent columns will be n by n. It will be square. And thus invertible. So we're going to use the idea of a basis a lot in the upcoming week and a half or so. And in fact, we're going to assign our variables to bases, which is the plural. We say that a variable is basic if it's associated with a column of a given basis. So to bring back our example from before, a equals 2, 1, 2, negative 1, 0, 0. When we multiply this by x, we're multiplying this column by x1, this by x2, x3, x4, x5, and x6, and so on. Well, not so on. That's all of them. So the basis we picked for the first one was just the first 3 columns, which means that our basic variables were x1, x2, and x3 were our basic variables. So every basis provides a unique basic solution to the system of equations when we set the non-basic variables to 0. So if you remember a few minutes ago, what we did is we said x4, x5, and x6 equals 0 because they are non-basic. That's what we did on the previous few slides. It turns out that if we have a system, if we're in linear inequalities, if we have equalities, not inequalities for our constraints, the basic solutions correspond to extreme points in the system. So basic solutions to extreme points. And we'll formalize that a little bit later. But that's very important for us. It means that we can actually start to enumerate extreme points for these very large and abstract many-dimensional LPs. So let's try a different basis. This is an easy one. The base is 2, 5, 6. So that's going to be the second row, the fifth row, and the sixth row. I want to put you guys in breakout rooms for just a little bit to think about what the basic solution to this is. And I'll make 2 breakout rooms. And we'll be in there for 5 minutes, I think. That should be plenty long. Bruh. Screen share. Drawboard PDF. Breakout rooms. Share. So did anyone find a basic solution that they want to share? All right. A few more seconds while I set this back up. Okay. Well, this is a slightly different because before our basis lined up with the halves of the matrix. Here it does not. So we're going to start a little differently, and we're going to recognize that x2, x5, and x6 are basic variables. Because, of course, we multiply that by x2, x5, and x6 when we're doing our matrix multiplication. So what we're going to do is we're going to set x1, x3, and x4, all of them equal to 0, since they're non-basic. And then we're going to think about a x is really, since x1 is 0, this column no longer exists or is no longer relevant. These three columns are no longer relevant since their associated variable is going to equal 0 in our solution anyway. So instead, we're left with row 2, or column 2, column 5, and column 6 times our basic variables, x2, x5, and x6. Oh, that's a little slightly wrong. That should be a 0. And this is equal to 2, 1, 1. Now this is already the identity matrix, so we actually get that much multiplication does not change our vector. And we're left with just x2, x5, x6 equals 2, 1, 1, which means that our basic solution x is 0, 2, 0, 0, 1, 1. And right now, it's not clear why this corresponds to an extreme point of our feasible region. But it's important that we discover in the next few lectures that it does correspond to an extreme point. Because we'll be using these bases to cycle through extreme points in our LP and compare them and find an improving direction in which to move and compare the next extreme point. So that is sort of the arc of the next section of the class. Starting on Monday, we will go over a method for expressing LP feasible regions as systems of linear equations instead of linear inequalities that we have now. So that'll be neat to have, and will set us on the path towards finally solving LPs. So that is all the material I have planned for today. So I will, as usual, stick around and answer questions if anyone has them, but you guys are free to go.